over the years I've come to realize that a lot of people have trouble with osmosis. And it's actually a very confusing process because of the terms that we use to describe some of the environments in osmosis. But really what osmosis is it's just the flow of water across a selectively permeable barrier. And the barrier we're going to be talking about in this class is going to be the cell membrane. Okay. Now what's happening in osmosis is water is actually flowing down its concentration gradient, just like all the other molecules do in diffusion. But when it comes to the terms that we use to describe what's going on in osmosis, the reason why I think people get confused is because those terms refer to the solute concentration, not the actual concentration of water. And those to the solute concentration versus the concentration of water are actually inversely related. So when you have a lot of solutes, you have very little water. When you have a lot of water, you have very little solutes. Okay? So looking at these terms here, we've got three terms, and they're actually relative terms. If you look at the term hyper, it says more or above. It's going to be more than something else. You're comparing two environments. And you're saying this environment has a higher concentration than the other. For hypo, that's less. Less than what? Less than something else, okay, that has a higher concentration. So we're going to be using these two terms together. And then lastly, there's iso, which means the same or equal. And we'll rarely see this in microbiology. You see that more in A and P or other organisms that practice higher levels of homeostasis. So when we look at these two boxes, we've got boxes of the same size. Box A actually has only 3 solute molecules in it versus box B, which has 8 solute molecules. So if we're going to use the terms hypo and hyper, first we will use hyper, and we say that box B is hyper to box A. And the reason why we say that is because hyper means more. It's more. It has more solute molecules than A. Remember, these terms deal with the concentration of solute molecules. And box A would be hypo to B because it has less solute molecules. Now if we were to take these boxes and fill them up with water, you can see that box A clearly has more water in it. And box B has less water in it. The reason why is because these solute molecules take up space. Okay, and you can see that when you have more solute molecules, that means that leaves less space for the water molecules to fit in there. Okay, so when we look at, as I said before, when we look at the concentrations of the solute molecules versus the concentration of water, when you have a lot of solute molecules, okay, you're going to have less room for water. Okay, very little water. When you have very few solute molecules, you have a lot more room for water. So if we were to take these two environments and connect them with the selectively permeable membrane or barrier, okay, it only lets certain things across. In this case, we're only going to let water across. Water is going to flow down its concentration gradient. We've already said that box A has more water in it, box B has less. So whenever we connect them with a selectively permeable barrier, we can see the flow of water from the left to the right, from an area hypotonic to an area that is hypertonic. So you need to remember this. Water flows from hypo to hyper, because in the hypotonic environment, since there are fewer solute molecules, there's a higher concentration of water. And when we look at in an actual example with microbes, okay, in this example right here, that oval, the green oval, is going to be the microbe. That's going to be the green is going to actually be the cell membrane of that microbe. And these little numbers in brackets, those are different concentrations. And these are not real world concentrations because the microbe is going to be a lot higher in concentration than 15. But we're just going to use nice simple numbers. Okay? So when we look at the flow of water, what we have to first determine, in order to determine the flow of water, is which area is hyper and which area is hypo. So we look at the concentrations. The microbe's 15, the pond water is 5. And remember, the term hyper means above. So you put that in an area that has a higher concentration. The term hypo means below. So in this case, this microbe is floating around in pond water. And so remember, our rule, water flows from hypo to hyper. Okay, so once we have identified our hypo and our hyper environments, then we know which way water flows from hypo to hyper. So in this case here, water is going to flow into the cell. Now, if too much water flows into the cell, think of the cell as a balloon. You blow too much air in the balloon, it's going to pop. Okay? And when too much water flows into the cell, all the cell contents are going to come out, and that leads to what's called osmotic lysis. When too much water flows in and the cell pops, that's osmotic lysis, and the end result of the osmotic lysis is cell death. And what's interesting is this is actually the normal environment that most microbes find themselves in. They're usually hypertonic to the environment. And when I say that, you should be thinking, well, how come they're still alive? And that's because they've actually evolved a structure to help them resist osmotic lysis, which we'll talk about a little bit later. Now, in this different environment here, we see that this microbe has landed itself on salted meat. Very, very different from the pond water. Okay. So the microbe's still 15, keep things consistent. The salted meat is at 1,000. Okay. So when we look at labeling hypo versus hyper, the salted meat actually has a higher concentration than the microbe. So all this is salted meat out here, so I'm just going to put it over here. Okay. That means that the microbe is hypo because it has a lower concentration than what's outside. The salted meat is 1,000. Okay, so water flows from hypo to hyper, which means that water is going to flow out of the cell. As water flows out of the cell, what the cell is going to do is it's going to shrivel up. Okay? And when it shrivels up, then one of two things can happen. Okay, it undergoes what's called plasmolysis, and the end result of plasmolysis will either be cell death, the cell can't take the loss of water, so it dies, or hibernation. It's going to be sitting there waiting in like stasis. You can guess what it's waiting for. If the lack of water actually put it into this state, it's waiting for more water. Okay. So that's it for osmosis. Hopefully that clears that up for you.